Next we'll start the variation of molar conductivity with concentration. Variation of molar conductivity with concentration. Now you tell me before starting the topic, if I increase the concentration of a particular solution, will the conductivity increase or decrease? If I increase the concentration of a solution, alright, okay, if you don't understand, I'll ask you something else. Concentrated HCl is a good electrolyte or dilute HCl is a good electrolyte? Or concentrated H2SO4 is a good electrolyte or dilute H2SO4 is a good electrolyte? You will say dilute. Sir, dilute. That means with the increase in concentration, the conductivity is going to decrease. Rather, with the increase in dilution, listen carefully, with the increase in dilution, the conductivity increases. Because just now what I asked you, conc H2SO4 or conc HCl is a good electrolyte. You said no, it is dilute H2SO4 or dilute HCl is a good electrolyte. That means with the increase in dilution, the conductivity increases. If I take concentrated H2SO4 and if I try to pass electricity through it, it will not be passed. Why? Because it's a covalent substance. It does not have ions which will conduct electricity. Correct? The free ions are not present there, hence it will not conduct electricity. But when you are adding water to it, due to the high dielectric constant of water, the electrolyte dissociates into its ions and as a result it starts conducting electricity. That means with the increase in dilution, the conductivity increases. That means we can say with the increase in conduction, with the increase in concentration, conductivity decreases. So hence what we can conclude, that is the molar conductivity of a solution decreases with increasing concentration. The molar conductivity of a solution decreases, just now I said, it decreases with increasing concentration. Correct. Now we will see this particular one with the help of a graph. So first we are going to see it for a strong electrolyte, then we are going to see it for a weak electrolyte. Because electrolyte is basically, right from the beginning I have said you, it can be either strong or it can be either weak. We are not concerned about non-electrolyte here, because non-electrolyte means it's not an electrolyte. What should I do with that, the substance which is not an electrolyte? What will I do with that? So hence we are basically concerned here with strong and weak electrolyte. So first I am talking to you about strong electrolyte. I am going to draw a graph and I am going to explain it, and I am going to find a formula also, you will see, that is from this particular graph. So listen carefully. What I am doing it here, that is finding it out, the cap M, molar conductivity. You know the unit of molar conductivity, just now I said you, ohm inverse, centimeter square, mole inverse. And it is square root of concentration I have taken it here, cap M versus root C I have taken it. Now concentration is a very small value, concentration, isn't it? If I take the square root, means it becomes still smaller. It becomes still smaller. If you draw a graph, you may get this sort of graph. This sort of. Will you understand anything? No. So for that particular purpose, to increase this concentration, the value, so that I can get a good quality of the graph, I will be getting it. So what I am doing, I am multiplying with a scalar quantity. You can multiply with 10 to the power 4, 10 to the power 2, 10 to the power 6, just to increase the value of concentration. Because concentration is a very small unit. Here suppose 0.1, 0.2, 0.3 in this way. So it will finish up in some small area. It is going to finish up. A small graph you will be getting it. Can you understand anything from that particular small graph? No. So just to increase the area here, just to increase the concentration here, so that a graph, it will cover a particular section. You know that in physics lab, you know that it is being always advised to you, your teacher advises you, that your graph which you are drawing it should cover 75% of the area of the graph paper. It should cover. Why? Why it should be 75? At least 75. Why? Because the teacher can see that what you have done it. So for that reason I have multiplied with this number. So this number, why I am saying you, because this number is going to vary from different book. In some book 10 to the power 6, some book 10 to the power 8, and some book 10 to the power 4. Any value you can take it. Just to increase the concentration I am taking it. Basic thing is that I am drawing a graph, cap M versus root C. That's it. A which electrolyte? Strong electrolyte. Let us say I have taken here KCl. I am taking potassium chloride. So what you will find is that, now see, concentration is increasing in this way, isn't it? Concentration is increasing this way. That means in this way, dilution increases. Dilution increases. If concentration is going to increase in this manner, dilution is going to increase in this manner. This, you can see it here. Okay, fine. So when you draw a graph, alright, of KCl, a strong electrolyte, you will be getting this sort of graph. This sort of graph you will be getting it. That means, see here, you are increasing the, what you can say, what is that? Dilution. Because concentration is increasing in this way. You are increasing the dilution. That means you are going and adding more and more water to it. Alright, clear? So dilution you are increasing. So what happens? See, the Cap M is also increasing. See the graph now. See, the graph is rising. It is rising. The graph is. Alright, the graph is rising. Clear? You can see that. It is rising, the graph. So which particular electrolyte? KCl I have taken it. Alright? Now, if you would have not done it, then what sort of graph you would have got it? This sort of. Steeply you would have rising it here. But here it is not rising steeply. Gradually it is rising. You can see that. Gradually. This is not the graph. This is the graph. Can you see it now? Now, the most important point you see. Have you understood, all of you? Are you following what I am saying? See, the dilution is increasing. So, the molar conductivity also increases. You will say, no sir, concentration is increasing. Fine. If the concentration is increasing in this way, the molar conductivity decreases. See, the graph is coming down. Whichever way you see, understand it, it's up to you. Now, why I have done it here, and what is this point? This point is cap infinity M. I am writing it out. This particular point, this point, this point. I will be writing it. Cap infinity M. Now, cap M is understood. Molar conductivity. What is cap infinity M? Molar conductivity at infinite dilution. At infinite dilution. This you need to understand. Understand it very clearly. When I am increasing the dilution, see here, when I am increasing the dilution, the molar conductivity increases, it goes on increasing in this way. If you still increase the dilution, practically, if you still increase the dilution further, molar conductivity is going to increase also further. But in a graph, can you show it? No, you have got a limitation. You can move up to this. You will say, sir, I will be taking a bigger graph. Are you take a bigger graph or a smaller graph? You have to end somewhere or not? You have to end somewhere. Still, the dilution is going to increase. Molar conductivity is going to increase. Further, it is going to increase. So, hence, this point I am theoretically considering it as that molar conductivity at infinite dilution, because in a graph I cannot extrapolate it further. What I said, in a graph I cannot extrapolate. I cannot extrapolate further. Can I go further? Theoretically, I cannot go further because the graph ends here. What will I do? But practically, I can do so. I can add more of water. I can increase the dilution still. And still the molar conductivity can increase further. But in a graph, I can't show it. So, I have to take this particular point as molar conductivity at infinite dilution. Means infinitely, what you can say, solvent is added to it. It is being made dilute. So here what is the solvent? Definitely water is being added to it. Understood now? We are considering it because theoretically we cannot extrapolate the graph further. It cannot be extrapolated further, the graph. So hence we are considering this point as molar conductivity infinite dilution, because you can see dilution increases, molar conductivity increases, goes on increasing. As you are going on increasing the dilution, it goes on increasing. But it has got a limitation. It cannot be increased further. I think it's clear. What is molar conductivity? Infinite dilution. Just understand the word. Infinite. We are considering it. That yes, this is the point which is infinitely dilute. Hence, this is the molar conductivity. Okay. So, in case of strong electrolyte, what you find that the molar conductivity increases with increasing dilution. Got it? That you have seen it? It's a very simple thing you have seen. And molar conductivity, you can say, decreases with increasing concentration. You can say that? Fine. Now, this particular, what you can say, observation was first of all observed by 3 scientists. What is that name? Huckel, Debye, and Onsager. Huckel, Debye, Onsager. And they gave an equation. They observed this particular phenomena. They did this particular experiment and they gave an equation. You don't require the derivation here. They gave an equation. What is that? Cap M is equal to cap infinity M minus B root C. Cap M is equal to cap infinity M minus B root C. This is the relationship. Cap M is the molar conductivity. cap infinity m is the molar conductivity at infinite dilution, C is the concentration root over of C, and B is a constant. So this is the relationship. They did the experiment is not there, derivation is not there in the syllabus. So just we need the equation. So equation I have wrote it there. So this equation was given for what? For which kind of electrolyte? Strong electrolyte, as you can see it. It is given for strong electrolyte. That is cap m is equal to cap infinity m minus v root c. Got it? Clear? So this is Huckel-Debye-Onsager equation. We can see that. Thank you very much.